always, we're going to start off with free body diagrams of each object. Um, so let's do the 2 kilogram object. 2 kilogram object certainly has a force of gravity acting on it. It's a little different here because the 2 kilogram object is not touching the ground, but something is holding it up. And what's holding it up is the friction between this and the block in front of it. So this is a strange situation in which the friction points upward. And if we think about it, if this thing isn't slipping downward, these two forces have to be balanced. What else is touching the 2 kilogram block? Well, the person who's doing the pushing, so the applied force, is touching the 2 kilogram block. And don't forget that the 5 kilogram block is also going to exert a normal force on it. So somewhat of a complicated free body diagram for the 2 kilogram block. Let's think about the 5 kilogram block. Of course, it has the earth pulling down on it. There's a force of gravity. There's the ground pushing up on it. There's a normal force. There's no friction between the 5 kilogram block and the ground, but the 2 kilogram block is pushing forward on it. And I'm going to call that Fn because that's what it is. It also happens to be the action-reaction pair to that normal force right here. This normal force is really the force on the 5 kilogram by the 2 kilogram, and over here it's the force on the 2 kilogram by the 5 kilogram. Those are equal and opposite pairs. So now that we have our free body diagram, where do we go from here? Well, one thing that I notice is that in order for the 2 kilogram block to not slip, the friction has to balance the force of gravity. And so that's a place to start, that the friction has to be equal to the force of gravity, which of course is equal to m times g. So let's find out what that's equal to. The mass of that block is 2, g is 9.8, that gives us 19.6 newtons. So we actually know that the force of friction has to be 19.6 newtons. So now let's assume that that is the maximum static friction and use that in the friction equation to figure out what the normal force has to be. So if 19.6 is the maximum static friction and the coefficient of static friction is 0.45, we can solve for normal force. And the normal force is going to be equal to 19.6 divided by 0.45. 19.6 divided by 0.45 is 43.6, let's say. And so that's helpful. Now we know that this is 43.6 newtons and this is 43.6 newtons. And that's really helpful here because it looks to me like we could find the acceleration of this block now very easily using acceleration equals net force in the x direction divided by mass. So the acceleration, if you add up the forces in the x direction, it's just that 43.6. That's it. Divide by this mass, which is 5. So let's find out what the acceleration of this is. So 43.6, it's still there in my calculator, divided by 5, 8.71. 8.71 meters per second squared. So this thing needs to have an acceleration of 8.71 meters per second squared in order for this thing to not slip. So now we can go back. Our goal here was to figure out this applied force. And you know, I know a common mistake is to think that the applied force is going to be equal to the normal force. But that would only be true if things were moving at a constant velocity or if it was at rest in the sideways direction. And that's not the case. It's accelerating at 8.71 meters per second squared. So let's just do acceleration in the x direction equals net force in the x direction divided by mass. We know that the acceleration has to be 8.71. We've got two forces here, the applied force that we're looking for minus the normal force that we just calculated and then divided by 2. And so that will allow us to calculate what that applied force needs to be. Just multiply that by 2, and then I'm just going to add 43.6 for an answer of pretty much exactly 61 newtons.